All right, let's go ahead and get started. It is 11 o'clock here in Central Time. You're in Dallas, Texas. And this webinar is going to be on SOLIDWORKS Simulation's new capability on Topology Optimization. My name is Arvind Krishnan. I work at GoEngineer as a simulation and 3D printing engineer, and do a lot of stuff on topology optimization. Part of my research was on it. So I'm excited to present to you a couple of housekeeping items real quick. If you do have any questions during, please do type them in the questions box in your GoToWebinar or the chat window, and I will make sure I address all of them at the end. And this recording will be available in our YouTube channel as well. So if you're listening to us on YouTube at a later time, then welcome to this. Thank you once again. Let's go ahead and get started with SOLIDWORKS Simulation's Topology Optimization. So this is the entire suite of SOLIDWORKS simulation tools, and part of Simulation Professional that is new with 2018 is topology optimization, which will be the focus of today's webinar. So to start off with, what is topology optimization? Optimization has been the central theme of engineering design for most of time. And part of my research, and I quoted this person, A.G. Mitchell, and the image on the left seems complicated, and I'm going to kind of break it down for you. But if you look at any bracket, if you look at any sort of part, the primary objective of that part is, imagine a point A where you have a loading, and point B where you have a fixture or some sort of support. The purpose of the part that connects is to connect the two and make sure that there is a proper transition of that load to the point of fixture. If you look at most brackets or any design, that's the primary purpose of it, right? And what Mitchell said, or what he did, was he said that the stiffest structure, which is the lightest weight to use for such a design to accurately transmit the load in the most efficient manner, is through what you call these lines, these solid lines that you see here, which are called maximum strain lines. So you see some of them that are kind of concave and some of them that are convex, some of them pointing downward, some of the lines pointing upward. And I'll just point out a couple of quick things about these lines. If you draw an imaginary line between this point of support and the point of force, which we call the neutral axis, you'll notice that all of these lines intersect that neutral axis at a 45-degree angle. And these lines, some of these would be in tension, some of them would be in compression. They intersect each other at a 90-degree angle. So this was major research that was done in 1904. And if we compare this to a problem that we commonly know, which is a cantilever beam, imagine a force on this blue dot on the left and a fixture on the right. The most optimum structure of that mimics what Mitchell told us in 1904. The only difference is, since 1904 to today, our computing power has increased drastically, and there's a lot of research been done on topology optimization. So now we have a computerized method to tell us where to place material in our designs to accurately come up with the best shape and the most efficient use of material. And that's what topology optimization is, where you create the lightest design by removing mass from the regions where it's not required to come up with the most stiffest structure possible. There's a bunch of examples out there. Buildings use it very often to come up with the best placement of weldments in their designs, such that it's placed in the most optimum location possible, and you're using the least amount of mass. Another one that you see on the top right is a bridge design. Once again, those lines that you see is going to be the placements of weldments or beams so that we can withstand the loads but use the least amount of material possible. In the last 5 to 10 years specifically, 3D printing or additive manufacturing is being used more and more as an end-use manufacturing method, where you can come up with complicated shapes, as you see in the bottom, in the middle, such that you can create much more lighter designs. You can combine 15-20 part assemblies into 1 or 2 complicated parts that can be 3D printed. But the higher cost of 3D printing is generally offset by your material savings, especially in applications like aerospace and automobile and defense. You also have other parts like this rotary application you see on the right bottom, where it can be machined the way it's shaped. So you're using traditional methods, and I want to make sure that I continue the focus in today's webinar on using existing traditional methodologies, because you don't need to implement topology optimization only if you're doing additive manufacturing. It can be used with a lot of traditional processes as well. So we'll be talking a little bit more about that. One thing that really brought topology to the forefront is General Electric came out with this engine bracket challenge about 5 years ago, where they threw out a design and they said, hey, can you go ahead and make this as light as possible, right? So this was the original design, and if I run this in SOLIDWORKS Simulation's topology tool, it tells me that, hey, this is where you want to place material. So that's what the new design looks like, and our mass has gone down by about 60% in this case, while still maintaining a factor of safety above the requirements. To tell you a little bit more about this challenge itself, the lightest design was actually down to 0.8. I believe 0.8, where it reduced about 84% of the mass. So if we go ahead and make more tweaks to this design, we'll eventually get there. Today, in this webinar, we're going to look at this antenna design. Thank you to Chroma Communications. I took this picture from their website. And our focus, so I went ahead and created a CAD model of this, and our focus is going to be on one of those legs in the bottom. So the antenna itself has a weight, and that weight acts as the loading. So we're going to focus our analysis on just this one stabilization leg, and we have some characteristics that we want to define for this. So the setup of our problem is going to be that we're going to use 1060 aluminum to define the material. The bottom hole is going to be fixed on the bottom right, and we're going to apply a remote load to define the mass, but it is a little bit offset too, so that it's a third of the weight because you have 3 legs, but it's a little bit offset, and hence any moments that are generated because of that, this remote load mass will take care of that. And I'm going to use split draw for manufacturing. I will talk about this a little bit more, but anytime you have any sort of casting methods, or even if you're machining it, this manufacturing of or adding a split draw constraint helps in accurately defining how you want that final shape to look like. So I'll show you a couple of examples of with and without this, so that it makes a better idea of what this constraint is doing. And lastly, I'm going to use a standard mesh to go ahead and mesh this, and then run the analysis. So let's go ahead and switch to SOLIDWORKS and see what this does. So like I said, here is my antenna, and let me go ahead and open up this part. And generally, your first step to doing any topology study is you want to do a static analysis. Okay, so like always, I'm just defining a linear static analysis. And the idea for this is, if your design does not work in its complete sense without removing any material, there's no way it's going to work if you remove material, because the stiffness of your part is only going to decrease. We just want to maximize the stiffness of the remaining material that you have. Okay, so we can go ahead and specify our material, right? And I also have my fixtures, which is that bottom hole over there. Now, before I define my force, I'm actually going to go to a previous study that I already did to define this force. And that's because I have some offset values that I calculated beforehand. So this force, how do I get to this? Let me show you that real quick. Under external loads, you have your force and all of that, but you also have remote load mass. And what that remote load mass does is it lets me apply that load on a remote location. So any load has location, magnitude, and direction, right? So the location of the load is this remote point, but we're going to remote load that. So we're going to apply an equivalent amount of force and moment on the face that you see over here. And so that location with respect to the global coordinate system is defined. And I also have my mass such that if I look at this from a orientation of the antenna, then that's the direction of the force downward for my location to simulate the weight of the antenna. So other than that, I've just done a standard mesh and I ran the study. This one doesn't take too long to run, and I see a max stress of about 1640 psi with a yield strength of 4000. So even if you want a factor of safety of 2, we have some room to play around with here. Let's go ahead and animate how this looks, and I have this animation is magnified about 250 times so that we can actually see it with the naked eye. It's not actually deforming that much. And once again, yeah, the factor of safety is about 2.4 right now. Let's go ahead and get this color chart all right. Okay, there you go. So you want to start from a safe point when you start your design. So let's go ahead to the next step, which is actually creating a topology study. Now, typically, if you're starting from scratch, you would again hit new study, and you would go ahead and select topology, and that lets you enter a name. I'm going to take a slightly different approach. Since I've already defined my material and my load and my fixture and my mesh, I'm just going to go ahead and copy this existing study. And I'm going to just say that this is now copied to a topology study as compared to another linear static study. And I can call this topology, let's say iteration 1, right? And that way I'm going to do the topology study, and once we hit the green check mark, we are now into a topology study. But since I started with a linear static analysis, I have the same material defined, I have the same fixture, the same remote load. Let's go ahead and look at this, right? And my mesh is also transferred over. When you're doing a topology study, there's a couple of additional steps you need to determine. The first one is, what is the goal of this topology study? There's a couple of options. One is the best stiffness to weight ratio, which is what we're going to use in our case. I want to reduce the mass by 40%. And what we're telling the software right now is reduce the mass by 40%, but remove 40% such that it least affects the stiffness. And that way I get the portions of my design that are contributing the most to the stiffness based on the direction of loading and the fixture is going to be removed. So once again, the regions of my design that contribute the least to the stiffness, the 40% that contribute the least is going to be removed from this design. Okay, that's the goal that I have. I have a couple of other goals that I can also define. One is minimizing the maximum displacement. So what this does is it's saying remove 30% of the mass such that you minimize the maximum displacement in the part. So let's say the displacement in the part right now was 0.25. Remove the 30% such that 0.25 increases the least amount possible. Okay. And the third one is going to be the minimize mass with displacement constraint. So what this is saying is something similar to the previous case, but it's saying remove as much material possible, but my displacement, my maximum displacement, should only increase by a factor of 1.2. So if you had a maximum displacement in the static analysis of, let's say, 0.3, after you remove material, it's going to go up to 0.36. But it's going to remove as much material possible such that the maximum displacement goes up to only 0.36. Now that we have spoken about the goals, I only added the stiffness to weight goal, by the way, and I've said that I want to reduce my mass by 40%. Let's talk about manufacturing controls real quick. First is add preserved regions. There might be some regions in your model where the stresses are not that high, let's say, but you still want them to be part of your final design. So let's say you have 3 or 4 different regions. We have multiple holes that help connect to other regions in the assembly where the stresses may not be that high, but I still want it to be part of my final model, right? I can go ahead and give it a preserved depth. So let me give it a depth of inches, let's say 0.75. So what this preview is showing me is the regions that are going to be part of my final model, whether there's a high stress region, whether it contributes to the stiffness or not. So no matter what, these regions are going to be part of my final part or of my final design. Okay. I think I hit the X, so let me go back and add that in. All right, so once again, we said inches and 0.75. There's my geometry preview, looks good. And lastly, I'm going to also talk about some of these additional options available. So one is specifying the thickness control. There's a lot of different manufacturing methods out there. Some of them recommend a minimum thickness to a region. Let's say some of y'all are in the aerospace industry that are going to be 3D printing or additively manufacturing such components, which have their own set of new design constraints. So if you're doing a metal manufacturing method, then there are some design guidelines on what the minimum thickness of your different regions should be. So you can go ahead and get that in using the thickness control, so that the final part that you see here is going to take that minimum thickness into account, and all the regions are going to be thicker than that. Another one is specifying the demold direction. And this is interesting because a lot of topology optimization has been commonly clubbed with additive manufacturing, but that need not be the case. Let's say you're doing sand casting or investment casting, or you're just machining this part, right? If you want a web in the middle and you have holes on the sides, you want to make sure that your mold can actually get out, right? And that's where you can specify the direction that you want to remove the mold in. So that edge defines my draw direction. And now when I hit the green check mark, I'm going to make sure that whatever final shape is there, I can use a mold such that it can go in from the sides and then it can be drawn out. Okay, let's go ahead and look at that again. There's also a pull direction only. What this means is the mold is going to be only drawn from one side, and hence any cutout that is in the center is going to go through on one side, and you can determine that. You can define that as well. And the third option is similar to the second one. Think of it as a stamping operation, but this time any region that it feels it needs to remove, it's going to remove everything behind and ahead of it. So all holes are going to be through holes. Any regions that it needs to cut out are going to go right through the model, and it's going to cut out the entire region through it. So that's, you add an additional constraint to the final optimum shape such that it can be machined. And I cannot stress enough how important these constraints are, because these constraints are what's going to help you not have like an empty region in the middle that is covered by material on the sides, which it looks great on paper, but I cannot make it then, right? So what's the use of that? I want to make sure that if I'm incorporating this, I use my existing manufacturing methods and that's what these help define. So I'm just going to keep that one demold split draw direction there, and the mesh is automatically carried forward. So theoretically, I could go ahead and run this analysis right now. Now, obviously, I've ran this beforehand. The static analysis runs relatively fast, but the topology study takes a little bit longer to run. So I think this one, I don't know if I'll get details. Let's see here. So I think this one took about 15 to 20 minutes to run. And let's go ahead and look at the results. So the one thing I want you to notice in these results is any of the holes that you have are going straight through, which means that these are regions that I can actually, once I cut out and machine, that they are actually of use to me as compared to just geometry that I cannot make. You'll notice that the mesh looks relatively coarse. If I go to a finer mesh, the study takes a little bit longer to run, but I might get results where I can remove more material. Okay, but this is an output. It's just a graphical output that lets me go and tells me where to remove material from. Okay, now what's important is next step. Okay, how do I actually go ahead and take this to create something meaningful, right? So how do I actually go ahead and post-process the result that I just got to something meaningful that I can use? All of us love SOLIDWORKS. We're used to the interface. We know how user-friendly it is. And we want to take advantage of that to actually create a final shape that we can use. We like our feature manager tree. We want to define our own regions. We want to define our sketches, regions to cut out, right? So we're going to go ahead and do that right now. One of the ways to exclude or to export this final shape is by going ahead and creating what's called an export smoothed mesh. It's basically going to take the mesh elements, use some smoothing algorithms to create a much more consistent profile to go from one region to the other, but it's still a mesh file. It's still an STL that you get at the end of the day. Okay. And I don't know about you, but I'm not very comfortable with having my final design as an STL. Okay, so there has to be a better method to do this. But if you want to just make a quick prototype, you can go ahead and do this and create, let's say, a 3D printed prototype out of this file. The method that I want to show you is what's called is using a feature in simulation that was introduced in 2017, and that is called the simulation display. Okay, so you can use simulation display, and what this does is it overlays that final result perfectly on top of my model, right? So if I rotate this model around, I still see that final shape, and what this does is it lets me go ahead and start a new sketch on this face and remove that material out, which is what I've exactly done. So let's go ahead and switch to a different configuration where I've gone ahead and now, for all the expert SOLIDWORKS users out there, y'all will probably cringe on me having underdefined sketches, but I've used some splines here. I've defined lines, but the beauty of this is, let's say you go ahead and actually define it. You can specify parameters. You can specify dimensions, and let's say your first prototype, your first iteration, you want to make some changes. Or if you send this to the machinist and he laughs at you and says that radius is too small, you probably need a bigger fillet there, otherwise I need 10 operations to do that. You can come in and actually change all of that with known parameters using the familiar SOLIDWORKS interface that all of you all are used to, right? So once we go ahead and do that, here's my final shape, and I can actually go ahead and create meaningful geometry from this. Okay, so if I go back to my SOLIDWORKS assembly, I can go ahead and switch my configurations to this. And once I do this, I have my final design that's a lot lesser in mass, right? I want to talk about one more thing though. How do I know that this actually works? How do I know that this design hasn't violated any other constraints that I have? And to do that, I want to do another static analysis on this part. So here's my static analysis on the topology part. So let me go ahead and pull that up real quick. And I want to make sure that I apply the same fixture, the same remote load, and mesh this part again, and then go ahead and look at what the results are, right? So what you'll notice is previously my stress results were about 1640. I've now gone up to about 1828. I'm still within my factor of safety of 2, right? So what this does is it helps me go ahead and improve my design, make it 40% lighter, but still ensure that I haven't violated any of my constraints, right? So this is my new design, which is way lighter, and I wanted to actually take the opportunity to then say that I don't have to actually 3D print this. I can go ahead and machine it. Another new feature in SOLIDWORKS was in 2018 was the introduction of SOLIDWORKS CAM. And in this case, I've used just a 2.5 axis mill, and a machinist colleague of mine went ahead and showed me an animation how I can go ahead and cut out my original design and cut out regions that are useless, go ahead and machine them out, and then also machine a lot of the holes on the inside. And actually, funny story, when I first created this, he came back to me and he told me, yeah, there's some fillets in here which are too small. I would have to do additional operations for that, so could you increase the size of that, right? And because I was inside the SOLIDWORKS interface, I could go ahead and do that to then create a final design which he could machine in just one operation, right? So that's where we are with this. So that was my initial design, and we went ahead, made some changes, made it much lighter, and now the new design is about 40% lighter, but it still has a factor of safety above 2, which was the original design requirement. That is topology optimization in SOLIDWORKS Simulation. Once again, thank you for your time. If you're listening to this in our YouTube recording, then we'll go ahead and end it here. If you have any questions, you can always email me or connect with me through LinkedIn. For our live audience, once again, thank you.